Staring at a complex algebra problem can be paralyzing. You are faced with a chaotic string of variables, exponents, and numbers, and often have no idea where to begin. But that confusion hides a predictable, logical pathway. For years, factoring has been taught as a loose collection of isolated tricks. Looking at this diagram, you can see the traditional experience on the left, staring at overlapping concepts like difference of squares, grouping, and sofas, and guessing which one might work. It turns math into a frustrating game of trial and error. There is an alternative. This flowchart, the algebraic blueprint, maps out a step-by-step diagnostic process. It uses the equation's own structure to dictate the solution. By relying on a systematic diagnostic routine, you remove the guesswork. The math itself determines the correct solution path every single time. The first node on our map is finding the greatest common factor, or GCF. The GCF is the largest number or variable that can be evenly divided from every term in your expression. To find it, you physically deconstruct each term. Here, we see the breakdown of 5x to the fourth, 35x cubed, and 10x squared into their smallest numerical factors and individual variables. Once you identify those shared elements, you extract them. Looking below the dashed filter line, you pull those common pieces forward to act as a multiplier, leaving a much simpler expression inside the parentheses. There is one strict rule here. The number 1 is always present in all numbers, so it cannot serve as a functional GCF. If 1 is your only shared factor, the expression has no GCF to factor out. Bypassing this initial GCF filter is a primary cause of failure. It forces you to apply complex algorithms to unnecessarily large coefficients, which significantly increases the probability of an error. Once the GCF is handled, we arrive at the triage node. This step focuses on one simple question: how many terms remain? That count routes the polynomial to its specific protocol. 4 terms mandate the grouping protocol. 2 terms suggest squares or cubes, and 3 terms signal a quadratic. If you have a 3-term quadratic, you run one secondary check. You inspect the leading coefficient, the a variable, to see if it is equal to 1, or if it is a larger number that complicates the factoring. Counting terms acts as an objective sorting mechanism. It converts abstract decision-making into a definitive numerical checklist. Sometimes you hit a specific mathematical roadblock, a quadratic expression where the leading coefficient is greater than 1. This makes the standard way of finding factors much more difficult. To handle this, we use slide and divide. In the first step, you temporarily slide the leading number across the equation. By multiplying it against the final term, you artificially create a simplified quadratic where the leading coefficient is 1. You then factor that simple expression normally. But because you multiplied at the start, you now have to undo your initial slide. In steps 3 and 4, you divide your new factors by that original leading number to bring the expression back to its original scale. Even stubborn, intimidating equations can be conquered through these structured sequences. By temporarily altering the expression, you bypass the difficulty and reach the final factored form. Let's run this polynomial through the system. 2a to the fourth minus 10a cubed minus 72a squared. Node 1 extracts 2a squared, leaving a squared minus 5a minus 36. 3 terms then route us to find factors of negative 36. Bringing the full factoring master protocol flowchart back on screen, you can see how these individual steps lock together into one integrated sequence. Mathematical mastery doesn't come from memorizing isolated tricks or blind luck. It comes from trusting a reliable, logical framework that tells you exactly where to go.